There are two types of error coefficients. One is static error coefficient and the other is dynamic error coefficients. In this lecture, we are going to focus on only static error coefficients and will discuss dynamic error coefficients in the next lecture. Static error coefficients focus solely on the final constant error as time approaches infinity. They indicate performance limits for specific inputs but ignore transient dynamics. Dynamic coefficients, on the other hand, are derived from Taylor series and model the full error evolution for slowly varying inputs. Static error coefficients are further classified into three categories. The first one is static positional error coefficient, which is associated with unit step input applied to a unity feedback closed loop control system and can be determined easily by the following procedure. We already know the formula for steady state error in terms of feed forward function, which is equal to limiting value when s tends to 0 of the expression s multiplied by Laplace transform of input variable r divided by 1 plus Laplace transform of feed forward function. As in the definition it is clearly written that static positional error coefficient is defined for step input, therefore rs is equal to 1 upon s. Now we have to simply put this value in the expression for steady state error, and afterwards we will shift the limiting expression in the denominator, which consists of the only variable in this expression. Static positional error coefficient Kp is defined as limiting value when s tends to 0 of the expression of the Laplace transform of feed forward function. This is how static positional error coefficient is defined. By putting the value of static positional error coefficient, we can also find the equation for steady state value in terms of static positional error coefficient, which will come out to be equal to 1 divided by 1 plus static positional error coefficient. The other static error coefficient is static velocity error coefficient, which is generally denoted as Kv. This coefficient is particularly associated with unit ramp input and can be defined in the same manner as we have defined the static positional error coefficient. Here, the Laplace transform of the input variable rs is equal to 1 upon s square, which is the Laplace transform of unit ramp input. First, we will put the value of this input signal in the formula of steady state error and then shift the limiting expression in the denominator. Also, the limiting value of s when s tends to 0 is 0 itself. That's why we have cancelled the first term in the denominator, giving us steady state value to be equal to 1 upon limiting value when s tends to 0 of the expression s multiplied by the Laplace transform of feed forward function. Static velocity error coefficient is defined as the limiting value when s tends to 0 of the expression s multiplied by Laplace transform of the feed forward function. Also, steady state value can also be written in terms of static velocity error coefficient, which will come out to be equal to 1 divided by static velocity error coefficient. The third and the last static error coefficient is static acceleration error coefficient, which is particularly defined for unit parabolic input. The expression for steady state value will remain same, only the input will change. Putting the value of input in the expression of steady state value and afterwards shifting the limiting expression in the denominator, we will finally get the expression of steady state value to be equal to 1 divided by limiting value when s tends to 0 of the expression s square into Laplace transform of the feed forward function. Static acceleration error coefficient is nothing but the denominator of this expression, which is limiting value when s tends to 0 of the expression s square multiplied by the Laplace transform of the feed forward function. Steady state value can also be written in terms of static acceleration error coefficient, which will come out to be equal to 1 divided by static acceleration error coefficient. In all the three cases, you might have observed that for three different acceleration coefficients, our inputs are fixed. In other words, we focus only on particular inputs in case of static error coefficients. The other thing is, it also includes only unity feedback system. And the third drawback is, it does not tell us how the error builds up with time. It simply tells us when the time approaches infinity, or you can also say it simply determines the final error value. These are the three limitations. of the static error coefficients, because of which dynamic error coefficients are preferred over static error coefficients. Now, you have seen it clearly that static error coefficient is dependent completely on the Laplace transform of the feed-forward function. And if we consider unity feedback system, then the type of the system is solely dependent upon the Laplace transform of the feed-forward function. Now, let us see the different cases depending upon the type of unity feedback system and different inputs. We will be limiting ourselves up to control systems of type 2, otherwise there is no end to that. Inputs are also limited to 3 inputs, which are unit step input, unit ramp input, and unit parabolic input. Now, let us try to find the value of steady state error in different cases. First, we will take the case of type 1 control system, and you try to solve the other two cases of type 0 and type 2 control system. First, we will consider the case of unit step input. The general expression of feed forward function is written where k is the magnitude of the Laplace transform of the feed forward function and ta, tb and so on are different time constants. Since we are considering for type 1, so there will be one pole present at origin. For unit step input, only static positional error coefficient is defined, which is equal to limiting value when s tends to 0 of Laplace transform of feed-forward function. If you try to find the limiting value of the above expression, since the s is present in the denominator, the answer will come out to be equal to infinity, and as such, the value of steady state value will come out to be equal to 0. So, we got the value of static positional error coefficient to be equal to infinity and the value of steady state value to be equal to 0. Now let's consider the case of unit ramp input. And just now we studied that for unit ramp input we have static velocity error coefficient, which is defined as the limiting value when s tends to 0 of the expression s multiplied by the Laplace transform of the feed-forward function. And after finding the value of static velocity error coefficient, we can also find the value of steady state error. I am assuming that you are having good knowledge of mathematics, particularly integral calculus. After applying the limits, we will find the value of static velocity error coefficient to be equal to k, which is the magnitude of Laplace transform of the feed-forward function, and the steady state value to be equal to 1 upon k. Now consider the third case. The Laplace transform of the feed-forward function will remain same as we have kept the type of the system constant. For unit parabolic input, we know static acceleration error coefficient is defined, which is equal to limiting value when s tends to 0 of the expression s square multiplied by Laplace transform of the feed-forward function. We will get the value of static acceleration error coefficient to be equal to 0 and steady state value will come out to be equal to infinity. We have found the value of steady state error for type 1 unity feedback systems for 3 different inputs along with static error coefficients. The term written in the bracket are static error coefficients. The more you are going to use pen and paper in your preparation, the lesser you will worry in the final exam. I have derived the value of steady state error for type 1 system. Now try yourself to find steady state value along with static error coefficients of type 0 and type 2 unity feedback systems. You have 3 minutes and 20 seconds. I hope you have found the values quite easily. Just check out your answer with this table. I don't think there is a need to learn this table, but the procedure and concept should be well understood by you. Sometimes theoretical questions also come from this table. Like, suppose a statement is written, the steady state error value is inversely proportional to static velocity error coefficient for unit ramp input. Obviously, this is true. For the unit ramp input, the only static error coefficient defined is static velocity error coefficient, and also steady state error value is inversely proportional to it. That's why this statement is true.